Like I mentioned this morning, um, this particular lab involves a couple of different things we've been talking about. It's going to be involving stoichiometry, which is basically looking at the ratios of how molecules interact with each other, and then trying to determine after a chemical reaction what the amount of products are going to be, and what the amount of, can we determine from that what the reactants were? Because what we're going to be doing today is collecting, we're going to be doing a chemical reaction, looking at the products of that reaction, and then putting the products back together to see if we can determine what the starting material was. And can anyone tell me what a hydrate is? Who's read the actual lab before? What's a hydrate? Very quiet. What's the difference between a salt and a salt hydrate? I think we all know what a salt is, a metal and a non-metal. But what's a salt hydrate?
Does it has hydrogen
Not just hydrogen.
and water? Or
Just
it has water?
It has added water, right? Even in the solid phase, it's still interacting with water. And so a hydrate is a part of an inorganic salt. So it doesn't, inorganic just meaning it's not carbon based, that we have a metal and a non-metal. So it has water integrated directly into the solid. So water is actually a part of the crystal, and it changes the properties of the salt in a lot of different ways. It makes it heavier because it's not just the metal and non-metal in there. You also have salt in the mass of the hydrate. It also will change its color a lot of the times. It'll change the texture. Generally, salts that don't have water in it are a lot more brittle. And so texture and consistency are a lot different. Generally, hydrate crystals are a lot larger and more uniform. And when you have anhydrous, which means without water, hydrous meaning water, anhydrous means basically you've driven all the water off. And so we can see that there is generally going to be a ratio of the particular salt we're dealing with and water. This is copper sulfate down here at the bottom. Copper sulfate pentahydrate. What does penta refer to?
5.
5, right. So it means that in a 1 mole of copper sulfate pentahydrate, you're going to have 1 mole of copper, 1 mole of sulfate, and 5 moles of water. And so when you measure the mass of copper sulfate pentahydrate, it has all those things in it. You have to include the mass of the water as well. And the reaction, this is a different kind of bond than we've dealt with before. And I'll talk about that a little bit later. But all it takes to break this bond is just some heat, which is different from a covalent bond, for instance. Just heat generally isn't enough to break a covalent bond. You have to have some sort of a reaction involving electrons being either given to somebody or taken away from somebody else to break a bond. In this instance, just the heat alone breaks it, sort of like an ionic bond. If you give it enough heat, you can force those two molecules apart. So in this instance, when we heat copper sulfate pentahydrate, we get the two products we get are a solid of just copper sulfate, and then the water is released as a gas. And so what we are looking for is the change in mass from the hydrate to the anhydrous form. And any difference should be the mass of the water. Because like with every chemical reaction, we have a conservation of mass. So if we start with the mass of a starting material, a reactant, and we measure the masses of whatever products, they should add up to be exactly the same thing. And it's that particular law that we're going to take advantage of today, because we won't be able to measure the mass of the water directly, but we will be able to measure the mass of the water, because the difference in the starting material and the ending material will be the hydrated form and the anhydrous form, and that difference will be the mass of water. So you can see that there's generally a big difference in what the anhydrous form and the hydrated form look like. This is the copper sulfate pentahydrate, and if the pentahydrate is on the right, you can see that it's this really pretty blue color. And you see a lot of this sort of color when you dissolve things into water, because obviously when you dissolve the salt into water, it becomes hydrated. But this is actually hydrated in the solid form. So you get these really pretty blue colors. But then on the left, when you drive off the water, you can see you drive off a lot of the color too. And so not only is the color a lot less, but you can see a big difference in the crystal formation. So you get these really, beautiful crystals on the right side, and then on the left side, you get sort of like really, it's more granular looking. You get a lot of difference. It's sort of like stuck together, and you don't see the sort of regular crystal formation that you would see in the hydrate. And every salt has a specific number of molecules of water that form when they crystallize. Some have 1 all the way up to 10. And so we call them mono, di, tri, tetra, and so on. And so each specific kind of salt has a specific name given to it, depending on how many water molecules are bound to it when the crystals form. So generally, if you take like a salt, dissolve it into water, and then slowly let it evaporate, a hydrate will form. And that's true even with sodium chloride, forms a hydrate as well. If you take just normal table salt, dissolve it in water, and then slowly let it evaporate, the sodium chloride that you get after that will be a hydrated form of sodium chloride, rather than the sort of anhydrous form we're used to seeing. So these hydrates form because of something called coordinate bonding or coordination bonding. This is something different than we've dealt with before. Generally, when we've been dealing with ionic bonds, where you have say, charged metal interacting with two charged nonmetals. And so this is a direct bonding based on opposite charge. And with ionic bonds, the chloride ions keep their electrons, and the calcium ion does not take the electrons from the calcium, from the chloride ions. It remains +2, and the chloride ions stay +1. And the interaction is just basically electrostatic charge. A covalent bond that we've learned about so far is when one atom brings an unpaired electron to another atom with an unpaired electron, and then they share those two unpaired electrons. And we call that a covalent bond. Well, a coordinate bond is different in that you have a metal, not always a metal, but in this instance, we're dealing with a metal. Let's say magnesium, because we're going to be dealing with magnesium in this particular instance. And what charge does magnesium have when it's an ion? What group is magnesium in?
2.
2, right. It has a +2 charge when it's an ion. So basically magnesium, we can see, is in the third row. So it's the second element in the third row of the periodic table. And we remember that in the periodic table, the first row has room for 2 electrons. The second row has room for 8 electrons. And the third row has room for 18 electrons. So magnesium, with its +2 charge, basically has no electrons in its outermost shell, none. So what it does in terms of coordination bonding, what coordination bonding means is that magnesium will interact with something that contains electrons, in this instance, water. Water has an oxygen with 2 lone pairs of electrons on it. And a coordinate bond is when one of the elements or compounds shares its pair of electrons with another element, but it still holds on to them. So it shares that lone pair of electrons, but it still keeps them close to the oxygen. So it doesn't donate them like it would in a regular covalent bond. Magnesium doesn't bring any electrons to this interaction, and oxygen brings both of them. So what happens is that magnesium ion will interact with a number of different water molecules in a very specific shape. And each metal has a different shape for these water molecules to interact. And so because each metal has a different shape for these things to interact, we'll see different amounts of hydration. We'll see 1 water, 2, all the way up to 10. I think even some have as many as 12 water molecules. And it's not always water. Sometimes it's ammonia, sometimes it's other molecules. In this instance, we're talking about water. So a coordinate bond is the sharing of a lone pair with another atom, but so both of the electrons from this bond come from one of the partners, which is different from the normal covalent where you have an unpaired electron. Generally, those are all unpaired electrons, and you have one from each atom. In this instance, you have a lone pair of electrons being shared, and they're not shared entirely because the oxygen still keeps them, but the lone pair gets close enough to the magnesium to sort of be part of its outer shell of electrons. And so we call that a coordinate bond. And just by heating the water, by taking this water now is in the solid state, right? The hydrate is a solid. So S brackets indicate solid. Well, if we add enough heat then the water will turn to a liquid, which we'll see in this experiment. You'll see the water go from a solid to a liquid to a gas. And then, because when you put the crystals, when you start heating the crystals, you'll see that they actually look like they're starting to melt and starting to bubble. First they'll melt, and then they'll start to bubble. The melting is the water then turning into a liquid. And then the bubbling is when it starts turning into a gas. And when it turns into a gas, then it will escape, leaving poor magnesium with its +2 charge, all by itself. So that's what coordinate bonding is. Any questions about that? Okay. So how are we going to measure this? So basically, it's like I said, it's a really straightforward experiment. We're going to take a mass of salt, and in this instance, we're using Epsom salt. So you should have a bag that looks like this. You've probably heard of Epsom salt before. People use it to people like soak their feet in it. And interestingly enough, you can also use it if you need to get your digestion moving. I'll just leave it at that. It'll just go right through you. So Epsom salt, it's just called that because I think it was just initially found in the city of Epsom, but it is actually magnesium sulfate with water included. So if we want to figure out how many waters there are, we would just weigh out a mass of salt. We would heat it, and then we'd see what the mass after heating was. That would be the anhydrous form. And then we would see what the difference in mass was. That would be the mass of water that's lost. And so we need to figure out how many moles of the anhydrous salt there are. In this instance, we've got copper sulfate. So we would figure out the number of moles of copper sulfate in the dried material, because in the dried material, or the anhydrous material, the only thing there should just be copper sulfate. So just using the molar mass, if we have a mass, we multiply that by moles over mass. That would be 1 over the molar mass of copper sulfate, and that would give us moles of copper sulfate. We then take the mass of the water that's lost. So the difference in mass between the anhydrous form and the hydrated form, that's the mass of water. So again, we take the mass of the water and we multiply that by moles over the mass of water, which is like 18.105 grams. That'll give us moles of water. So at the end of this calculation, we have moles. We would have moles of copper sulfate. That's how many moles of copper sulfate are left in our anhydrous mass of salt. And then we would have our mass of water. Convert that to moles. Then we have a ratio of copper sulfate to water. Once we have the ratio of copper sulfate to water, then basically we have our formula for the hydrate. So what would be our ratio between these two? We have 0.0199 moles of the copper sulfate, and we have 0.0999 moles of water. What's that ratio? So it's going to be more water than salt. So we would put the water on the top and the moles of copper sulfate on the bottom. What's our ratio of one to the other? For instance, that's really close to 0.1, and that's really close to 0.02. What's my ratio there?
Is it 5?
5, right. The ratio will be 5-1, meaning there's 5 waters for every 5 moles of water for every 1 mole of copper sulfate. So what would we call the hydrate of copper sulfate? We would call it copper sulfate what hydrate?
Oh, pentahydrate.
Penta, right, and that's what it is. Pentahydrate. So, I mean, we would like to get results this good. We're not really, don't really know what each one of us is going to get, but that's what we're basically looking for. We're looking for what is the ratio of moles of water divided by, in our instance, moles of magnesium sulfate, not copper sulfate, because we're dealing with magnesium sulfate this time. So we're just looking at the ratio again of the water that's lost to the, in this instance, make our magnesium sulfate left over. And you can see that magnesium sulfate is a heptahydrate. What does that mean? How many waters is that for magnesium sulfate?
7.
7, right. So what we're looking for is a ratio of 7-1. Moles of water divided by moles of magnesium sulfate. So this is what we're going to need to do this reaction. So we should have our bag of Epsom salt. We have a wire stand. Everyone should have the little wire stand. We're going to do this reaction in triplicate because we normally, when we're doing these sort of analytical experiments, we want to do them in triplicate at least. So we're going to weigh out our hydrated salt into these aluminum weighing dishes, and then heating these up. And we're going to be heating them using sterno. And anyone who's been to, I don't know, like a wedding reception or something will definitely have seen these things, like, you know, under dishes, keeping them warm. Basically what sterno is, it's just a gel of ethanol. So when you burn ethanol, you don't really see much of a flame. If anyone's watched like auto racing, has anyone ever noticed, like if there's like a fire in a car race, you'll see sometimes there'll be a crash and you'll see the driver get out and he's like waving his arms around and you don't see anything. Well, the sad truth is that he's on fire or she's on fire and you can't really see it. So in the sterno, they put a little color in so you can actually see the flames. It's kind of dangerous if you don't know something's burning, you can, like, you know, put your hand on it. So we've got the can of sterno, and that should burn for at least 45 minutes, which gives us plenty of time to do 3 experiments. And then we'll just need our balance. And these forceps that are given, I wouldn't use them. I mean, if you got nothing else, then use them. But I've got a pair of metal forceps because the plastic ones will melt. That's the honest truth. I mean, because these things, you're heating these under a fire, you know, so they're going to get pretty hot. And so you put plastic on them, you know, they tend to melt. So I have these, if you don't have, like, you know, tweezers or something like that, would be better. If you don't have anything, just use the forceps. They'll melt a bit, you know, live with it. Or an oven mitt, or, you know, a pair of tongs or something in order to move these around, because these are going to be really, really, really hot and you're going to want to be careful. And it's really important to wear eye protection today, because we're going to be dealing with fire and potential material, like, you know, spitting out at you from, because remember, we're taking solid water, turning it into a liquid, turning it into a gas. So it tends to, you know, spit out of the aluminum dish when we're heating it. So pretty straightforward experiment. We want to label each of our dishes 1, 2, and 3. We'll take the mass of each one without anything in it. Then we're going to add between 0.3 and 0.8 grams. And then remember, you don't have to have exactly 0.3 or 0.8, but somewhere in between, but you will want an accurate mass. So when it says, between 0.3 and 0.8, don't use just a single decimal. You want at least 2 significant digits in your mass. You want an accurate mass, or you won't get an accurate number of moles of water. So then we subtract the mass of the empty dish, and that's going to be our mass of hydrate. So we're going to need our mass of hydrate. That's our starting material, because that's our salt plus our water. And then we're going to heat these underneath the sterno can for about 10 minutes. And you're going to hear it crackle and pop and everything else. Let it go for at least 10 minutes till basically things stop happening. The melting has stopped, the popping has stopped, and generally nothing is happening that you can see. The crystals that are in the dish don't change anymore. That basically means that all the water has been driven off. So then you take it off the heat, let it cool down for a couple of minutes so you don't burn yourself or damage the balance, and then take the mass of the dish. Now the mass in the dish will be the dish plus the salt alone. So you subtract the mass of the starting dish, and now you just have the mass of the salt by itself. Now the difference between the mass of the hydrate originally and the mass of the salt alone will be the mass of your water. And once you have the mass of the water, you have the mass of the salt, you know what the molar mass of magnesium sulfate is, you know what the molar mass of water is, you calculate the number of moles, and then you get the ratio. So this just goes through exactly what I've just told you. At the end, so you do this thing 3 times. So each one, like I said, it's going to be a fairly brief experiment, because it's only going to take about 10, 12 minutes to do each one. Allow them to cool, and then get the masses again. So you calculate the masses of water and salt, you calculate the moles of water and salt, and then get the ratio. So here's where you're going to put your data in. So each dish should weigh approximately the same. I can't remember exactly what the mass is. I think it's around 3 to 5 grams, something like that, maybe 7. So this will be your starting material. And then the difference will be the hydrate. So just the dish, the mass of your dish plus the starting material, the difference is the hydrate. After the heating, that's dish plus salt. Subtract the dish, then you've got mass of salt. And then the difference between the dehydrated mass and the hydrated mass is the mass of the water. And then from that point, you just get moles of salt, moles of water, and then the ratio of water to salt. And what ratio should we have for this experiment?
Uh, 7 to 1.
7 to 1, that's right. This is a heptahydrate. So you should be seeing fairly close to 7. So, I mean, don't worry if you don't get exactly 7. Don't worry if you don't get it exactly right, but we're looking for approximately 7. So if you do this 3 times, take the average, hopefully you should get fairly close to 7. I think most people got it between like 5 and 7. You'll get less if you don't heat it to completion. You'll drive off less water and you'll see fewer moles of water, obviously. And if you lose some, let's say some of the salt actually pops out of the dish because, you know, snap, crackle, and pop or whatever, then you'll see greater than 7 because you'll get a loss in mass of both water and some of the salt. And then you'll write that down as a loss in water mass only. So that's one of the, when you're asked to determine potential errors, those are 2 of the potential errors in this particular experiment. So any questions before we get started? I was just going to answer any questions and then give you some time to get all your stuff together.
I haven't seen the template for this lab.
Oh, have I not put it in yet? Oh, I'll do that. I'll do that right at the end of the lab today. I'll put it in there.
Okay.
Yeah, thanks for reminding me. Let me write that. Yeah, sometimes get ahead of myself. Okay. Anything else? All right, let's take about 10. And then, so let's say 2:45, we'll come back together and we'll have all of our goggles on and we'll get started, okay? All right. I will see you in a minute. Everyone, goggles on. So, start with our bag of Epsom salt, or magnesium sulfate. Then you can break up some of the bigger crystals. I found like the big ones will tend to pop when you start heating them. So remember, we want between 0.3 and 0.8 grams. So first I get the mass of my dish. Oh, it's a lot lighter than I thought. Remember, aluminum is a light metal. So the mass of my dish is 1.29 grams. So I'm going to want between like 1.59, 2.09, somewhere in there. Just get an accurate mass. That's a pretty good amount. So my mass of the dish plus hydrate now is 1.74. I'll write that down. Then I got my sterno here. Pop that thing open. You can just use like a knife or something to pop that open. You can see it's a nice green color, so you'll get nice green flames out of this. Yeah, and you can smell the ethanol, so it's quite clearly ethanol. And then just light it on fire. So you see the flame, you can't really notice. You could sort of see the flame, but not really. So be careful with this stuff. And it also crackles a little bit. Then I'm just going to put my crystals on top and start the clock. Now you should be making notes of what you're seeing. So the first thing I'm seeing is bubbling taking place. And the crystals are starting to melt. Now you don't want to get too close to this because, like I said, it will, sometimes these things will just pop like popcorn, just come right out of the. So while number one is heating, you can also weigh dish number two, weigh dish number three, and then add your hydrate to each of those and get their mass as well. So then as soon as the first one is finished, you can pop the second one on. And then as soon as that one, just pop the third one on. So also starting to see the difference in the way these crystals look. You can see originally they sort of have, you can almost like see through them. They're almost like have a transparent quality. But now they're starting to get this sort of white opaque color, which is a lot different. Well, I mean, it's a white color, it's opaque. It's not translucent like it was before. And that melting is basically stopped. And I'm seeing popping taking place with the crystals. You can see them every once in a while they start to pop because there's some water trapped in the middle of a crystal that's being released. Got about another 5 minutes to go. So those of you without your cameras on, you just make sure you got your goggles on, just to be on the safe side. Thanks, Taylor. Yeah, you may want to put something under the sterno can because it gets pretty hot. So you don't want it to like directly on a tabletop or anything, because it may leave a mark. I'm hoping that what I've got under here is going to be enough. My wife spent like 3 days refinishing this table. She's going to be really angry at me if I leave a ring on it. Yeah, so the changes that take place pretty quickly, but don't think that they're finished because it still takes quite a long time to make sure you've got all the gas removed, because some of these crystals are pretty big. They're not uniform in size, particularly when some of them, if you have a lot of them that are close together, they'll melt into sort of one big crystal. And then it may take some time to get all the water out of it. So Dee Dee, remember to put those over your eyes, right?
Oh, I'm sorry,
Yeah.
Professor.
Yeah.
On the number 3, like it's saying measure approximately 0.3 to 0.8 gram. So
Right.
is that both?
So
Or
you
should I?
want more than 0.3 grams, but less than 0.8. That's all that means. Get an accurate mass.
Okay, so that include the aluminum dish too, like both
No,
together?
no. You
Just
want
the
whatever
salt,
the
right?
weight of the dish is plus 0.3
Oh, okay.
to 0.8. Yeah.
Okay.
So if
Thank you.
this was like around 1.3, so you want a mass of between like 1.6 and 2.1, somewhere in between there. See how much longer. I have another 2 minutes to go. So at the end of this, if you haven't used, if there's still some gel in the sterno, all you need to do is just basically just put the top on it. Don't push it down. Just put the top back on it and just let the oxygen basically be used up inside, and just don't touch it for like about 10 minutes. If you push it down, the gases are just going to make it explode. So you don't want to do that. Just basically choke the oxygen off with the top. Just settle it down on top of it and then just leave it. Or just let it burn out. Although I found generally these things normally will burn longer than 45 minutes. So there's usually a lot of fuel left in these. Yeah, the shapes of these crystals are interesting too. Some of like the individual crystals, you see these crystals are sort of, cubic shaped, like, most salt crystals are. And if you have them one all by itself, they seem to turn into like a perfect sphere when the water gets lost. And that most of the crystals are now round rather than being cubic. Right, I'm just going to let these go a little bit longer. So has everyone weighed out their 3 while they're heating the first one? Ryan's on top of it. I can actually see you today, man. You changed your lighting. Used to be working in the dark.
I just switched sides.
You look like Batman or something, like in the cave. I'm not really hearing any more sounds from I'm still hearing the cave. The sterno will still crackle, but I think any of the crackling sounds are coming from the sterno itself and not from the Epsom salts. I think so. It's really hard to know when this is done. So if you want to let these go for like 12 minutes rather than 10, that's not a problem.
For the part of the table that says Epsom salt heated dehydrated mass, we subtract the. Is this where we subtract the mass of the aluminum plus the dish?
Right. So that will be the mass of the cooled off dish with the anhydrous now, hopefully anhydrous salt in it. So we're going to let that cool. So what should be in the dish now should be the anhydrous form. So we'll get that mass. We'll subtract it from our original mass of the dish, and that should be our dehydrated. That should just be the mass of the the magnesium sulfate by itself.
Oh, okay. So it's
Yeah.
gonna be the mass of the aluminum dish and the Epsom salt after heating,
Yeah.
subtracted by the mass of the original aluminum dish.
Right, because that's generally will be you'll get less you'll get better number that way. If we try to like get if we tried to weigh the mass of the salt that's in here, we may have some that's like just stuck to the dish and we can't get it off. So it's just better just to subtract the mass of the dish rather than transferring it and measuring it again. I'm pretty sure that's done. So I'm going to take that off using my metal and just let it cool for a minute. I'm also going to take the top and just put it back on top of the sterno can and just let it burn itself out. Yeah, if you just put the top back on for just a couple seconds, it's out. I'm not going to close it tight though, because it's still hot. So I'm just going to let it cool for like about 2 minutes or so.
So, Professor,
Yeah.
we're only using two significant figures, right? Like for
Your
the mass of
your
aluminum,
mass,
1.3.
yeah, your mass is only going to have 2 significant figures in it. So yeah.
Okay.
But remember, when you're doing your calculations, use as many significant digits as you like until you get to the end. So then our ratio will be, then that will only be able to report with 2 significant digits.
Okay.
But we're going to use more than 2 significant digits for the molar mass of the magnesium sulfate and the molar mass of water. So I'm going to put that up now. All right, so the mass of my dish was 1.29 grams. Dish plus hydrate equals 1.74 grams. So my hydrate mass is 0.45 grams. Dish plus salt anhydrous. That's what I'm going to measure after it's cooled down.
And then for the mass of the water, we're subtracting the original mass of the Epsom salt minus,
Yeah, it would be our dish plus the hydrate minus dish plus the salt. The only difference will be the loss of water. You could also, take the mass of your hydrate and then take the mass of the salt. You can do that also. You'll get the same number. So this is cooled off. Yeah, it'll cool off pretty quickly because we are dealing with a metal. And not only do metals conduct electricity really well, they conduct heat really well. So they gain heat really fast and they lose heat really fast. I'll make sure I got triple zeros on my scale. Put it on there. And now the mass is now 1.53. So the mass of my salt is this mass minus the dish. So the mass of my salt is 3 minus 1.29. So the mass of my salt is 0.24 grams. So the difference between the hydrate and the salt is the mass of my water. So the water mass is 0.21 grams. So this is how much salt I've got. This is how much water I've got. So then I'm going to use those to figure out moles. So my salt, 0.24, water, 0.21. So let me clear that out. So my salt is 0.24 grams. Now I want to convert that to moles. So if I want to convert that to moles, do I put moles in the numerator or the denominator?
Moles in the numerator.
That is correct. Now, interestingly, moles of what? What is my actual salt here? Is it magnesium? Is it magnesium sulfate? Or is it the magnesium sulfate hydrate? Which one is it? What do I want the molar mass of?
Would it be just magnesium sulfate?
That's right. It's just the magnesium sulfate because we've driven the water off. So it's not magnesium sulfate hydrate anymore. It's just magnesium sulfate. Excellent. So I want the molar mass of magnesium sulfate. So I can either calculate it or I can cheat and look it up on the internet, which is what I did. And so the molar mass of magnesium sulfate is 120.366 grams per mole. And it's perfectly fine. If you're writing a lab report, you don't have to calculate the molar mass thing. Just look it up. It's not a test, right? So we can take advantage of these things. So 1 mole of magnesium sulfate is 120.366 grams. So that cancels out my grams. I'm left with moles. And I get 0.0019939. And again, I'm not going to bother with rounding. I'm not going to do any rounding right now because I don't have to. And I shouldn't because I don't want to limit my precision. So I'm going to use as many digits as I damn well please. So that's moles of salt. Next, I want to calculate my moles of water. So my water, I had 0.21 grams. Molar mass of water is 18.015 grams per mole. So again, I want moles of water. This isn't magnesium sulfate, it's just the water. I put the mass, molar mass of the water down here. I get rid of my grams. I'm left with moles of water. That's what I want. And I get 0.011657 moles. So you obviously you should have more moles of water than you do moles of salt because it's a heptahydrate. There's more moles of water than there is moles of salt. So then to get the ratio, I just want my ratio of water to salt. And that is 0.011657 moles. Whoops. Damn dyslexia. Anyone else have a little dyslexia? I'm constantly switching numbers back and forth, which is why I always double and triple check my calculations in the lab. Minus my 0.00199939. So that ratio is 5.846. So then we round that to 2 digits because I've only got 2 digits in my mass. So I would get a ratio of 5.8 or 6. So I'm off by 1. So maybe I just didn't. So some things I could have done differently. Could have made sure that I distributed my crystals more evenly across the aluminum pan. I think that really helps. If you have too much of them in the middle, they tend to sort of all melt together and then form these like great big crystals, which may keep the all the gas from escaping if the crystals are too large. If they're spread out more evenly, I think you get a better result. So instead of getting 7-to-1 ratio, I got a 6-to-1 ratio. So close, but no cigar. So I would have said it's a hexa hydrate rather than a hepta. And I think that's pretty much exactly what I got last term as well. 6 rather than 7. I think most people got 6 rather than 7. So that's the two things I would suggest is spreading your crystals out a little further apart from each other and maybe heating it for slightly longer. I think I let it go for like 12 minutes. You can let it go for a little bit longer if you like. But that's how you can see that these calculations are fairly straightforward. Just mass of salt to moles of salt, mass of water to moles of water, get the ratio. So I would think anything from like, 5 to 8 would be pretty good. Remember, we're shooting for 7. So if someone asked me what my potential errors were, yeah, not letting them dry enough, or potentially forming these great big crystals. I'll let you see what mine looks like. So here's what my crystals look like. You can see that, yeah, some of the ones in the middle are really, really big. And I think that possibly there's still some water in there that just didn't get a chance to escape from the middle of these big, big ones. The small crystals, I'm pretty sure, have lost all the water. So if you could get them spread out, I think that would probably that would help in that regard. And that's it. So basically just we're going to be doing a lot of these sort of calculations, doing ratios of different things, because that's what stoichiometry is, basically looking at ratios of products and reactants. So Thursday, get ready for a whole bunch of stoichiometry, and then a bunch of gas law after that, and then combining the two. That's always fun. So any questions about how to proceed? Yeah, it's a lot of people have their glasses off already. You've done all 3 of your heating, or that was fast. Man, Taylor, you're just racing through this.
It helped. I measured everything beforehand, so that
Sweet. Okay, so what? Any results yet?
Most of my calculations are all the same. So for the mass of water, I got 0.14 for like all 3 of them. So that makes most of my ratios the same.
And
Actually, it makes all of them the same.
cool. So what ratio did you get?
I got the same. I got 5.846, the same as yours.
Interesting. Let me double check and make sure this actually is a heptahydrate. Yeah, it says it's hepta. We're in trouble. But hey, 6 divided by 7, that's only about like a, is that a 14 degree error, 14%? That's not too bad. Basically anything less than 25, I consider a victory. Anyone else have any results yet?
I got my first one. The ratio was 7.4.
Oh, nice.
Yeah.
7.4. Damn, she's closer than us, Taylor. I don't know what. She's going to get a better grade than either of us. All right. Any other questions before we wrap it up?
Oh, sorry.
Oh, go ahead. Jessica, you had a question?
No, I was just gonna show how mine look. The first
Oh,
one.
yours look about the same, actually.
Yeah.
Huh. So maybe the problem wasn't with the bigger crystals. Maybe we just suck at chemistry. Can anyone else do better than 7.4? Looks like your record's going to stand, Jessica.
I think the second one is even closer.
Oh, now you're just bragging. Now you're just flossing. So you got even closer than 7.4.
Yeah, I'm gonna finish calculating, but I think so.
Oh man.
Because the mass of aluminum and the salt after heating, it's a little lower. So
And you use the same mass of salt each time.
no, I did it different. It's different.
Okay.
But like when I wait after heating, it's a little less than the first one, the second one.
Okay.
I don't know. I don't know. We'll see.
That'll be even more water loss then. I guess we'll have to see. You still calculating, Ryan?
For the second one, I actually got close. It was 7.45 for the ratio. My first one
Nice.
was 4.78.
Ooh, ouch. That's why we do it in triplicate, man. That's exactly why we do things in triplicate. You average them out, you're probably gonna do pretty close. All right, so you can just dispose of these. I mean, there's nothing, magnesium sulfate is not dangerous or anything. And then you can just keep the rest of this and soak your feet in it. You know, just don't eat it, because like I said, this is a fairly powerful laxative. So be careful. Not a salt you want to sprinkle on your food, believe me. Probably tastes fairly nasty too. All right, any other questions before we wrap it up? Mac, how'd you do? You still with us? They must be gone. What about you, Jocelyn? How are you doing?
Doing good. I'm on the third one now, and I just need to do the ratios left.
Okay, cool. Wilhelmina, did you get a result yet?
I'm still doing the calculations,
Okay, have you?
and on the third one, yeah.
Well, the gauntlet has been laid down. We got 7.4 and 7.45. Obviously, you're a better chemist than I am. All right, everybody. I will see you. Yeah, I will put the templates on Canvas right now while I'm thinking about it, and then I'll release the workshop sheets tomorrow for Thursday. And remember, I'll go over the last two questions because they seemed like damn near impossible for everybody. So I will go through them with you to show that they're not impossible, just really difficult. All right, everyone. I'll see you soon. Again, remember, I also have office hours tomorrow if you have any questions about any of this stuff, okay?